For our second Monte Carlo simulation example, we're going to solve a single period inventory model called championship hats. This is from section, section 3.2.3 of the textbook. And championship hats basically is a problem where your favorite sports team, like in this case the Cincinnati Reds, I guess, have won their league championship, and you are a vendor selling hats. And the decision you have to make is how many hats do you purchase, because you purchase the hats ahead of time. And so we have some data here. The wholesale cost of a hat is $11.95. The retail price, what you sell the hat for, is $16.95. So we make $5 profit on each hat that we sell. However, at the end of the peak sales period, if we don't sell all the hats, then the hats go on clearance, and the clearance price for a hat is $6.95. And so for the clearance hats, we actually lose money. So we make money for the retail hats during the peak period, we lose money for the hats during the clearance period, and our decision is H, how many to order. How many to order. So in thinking about this decision of how many do I order, if I order too few, what happens? Well, we have unmet demand, which essentially is lost profit. If we order too many, what happens? Well, if we order too many, then we lose money because we have lots of hats left over. Lots left over. Lose on the clearance. So once they go to the clearance table, we lose money. So the question is, well, how many do we order? Now, one thing that clearly leads into this decision is what's the demand? In other words, how many am I going to sell? Well, if we knew how many we were going to sell, we would just order that many. There'd be no point in ordering any more or less. Unfortunately, the demand is a random variable. So this is a random variable. And in our case, it's distributed uniformly between 1,000 and 5,000. So we don't know how many we're going to sell, but it's going to be somewhere between 1,000 and 5,000 because it's uniformly distributed. All values, we're assuming that all values are equally likely. So let's call our demand D. Again, it's a random variable, so we don't know exactly what it's going to be for any instance of the problem. And now let's see if we can figure out what the profit, which we're going to call Z, as a function of H, because clearly the profit is going to depend on how many we order and then the demand. And so our profit we can represent as follows. We get some revenue during the peak period, peak revenue plus the clearance revenue, minus our cost. And so the peak revenue, we get R, or $16.95, for the number that we sell. Again, we don't know how many we're going to sell. It turns out that it's going to be the minimum of the demand and how many I order. So if the demand is 2,000 and I order 1,500, then I can only sell 1,500. On the other hand, if I order 5,000 and the demand is 3,000, then I can only sell 3,000. So that's where that minimum comes from. The clearance is the maximum of how many I order minus the demand, so the leftover values. And if those leftover values are negative, in other words, if we didn't order too many, then we don't sell any on clearance. Minus the wholesale cost times how many I order. So our profit is represented by this expression where R is known, $16.95, C is known, it's $6.95, W is known, it's $11.95, H is what we're trying to decide, and D is a random variable. Because D is a random variable, that means ZH is a random variable. So ZH has some distribution. I'd like to know that distribution, but I don't. This makes it a perfect application for Monte Carlo simulation. So I can sample my value, an observation of demand. Once I sample the value of demand, I can then solve for ZH, and then I can simply repeat that process for the number of times equal to the number of replications of my simulation that I'd like to do. Now in the book, this problem is solved in Excel, and so this is model 0303.xls. So you can see the model here, and you can see that in the book model we sampled different values for the we solved for different values of h. So we tried h at 1,000 and 2,000 and 3,000 and so on. For this video, what I'm going to do instead is we're going to solve the problem programmatically. So I'd like to look at creating a program that will execute this Monte Carlo simulation. So the first step that I'd like to do is I'd like to create the pseudocode for our Monte Carlo simulation. Our simulation is pretty straightforward. I'm going to track my number of observations, which I'm just going to call create a list or an array called OBS for observations, and I'm also going to specify the number of replications. Reps, let's say we're going to do 1,000 replications initially. So I simply iterate through my 1,000 replications. So I'm just going to say for I in range num reps, I'm going to sample D. Right? And so D again is uniform between 1,000 and 5,000. Then I'm going to solve for Z given my H value. So I have to specify an H value. Let's just say up here, let's just say we set our H value at 3,000 to start with. And my Z, I simply use the expression that I have developed right here. So I'm not going to copy that down, I'll just put it there. And then I'm going to append that to my list, OBS, append Z. And so when I come out of my loop, my list observation OBS has my 1,000 observations, and so I can then just simply print the mean of OBS and then print the standard deviation of OBS also. So again, my basic procedure is I define H, I then set up a list or an array for my observations, I specify the number of replications, and then I iterate for the number of replications. I simply sample my D value from my uniform distribution. I solve for the profit given the corresponding value of D that I sampled and H that I set. I then store that value, and when I come out of the loop, I then print the mean and standard deviation. Now the specific implementation that you use or the language that you use will dictate what these individual statements look like how I define the array and how I sample the random variates and so on. But in my example, I chose to implement this using Python. And so here's my sample code that we can see here on line 40. I simply set the H value, specify the number of replications as I specified, loop through, and then I just print some information on how many replications that I ran and the H value. For the standard deviation and the mean, I have created simple functions to do that. So my mean function returns the mean, my standard deviation function returns the standard deviation, and when I execute my program, this is a news vendor initial, it ran my 1,000 replications and reported to me that my average was a little bit over 12,800. So if I run this again, I'm going to get different values, so I've just resampled another 1,000 and another 1,000 and so on. And so one advantage of doing this programmatically is it's very simple to make changes. So for example, if I want to do 5,000 replications, I can simply increase my number, my in reps, and then when I run, I've just run 5,000. So I'm becoming more confident about my results, as we know, because the more we run, the better our results are. Now, of course, a couple of things here. One is that our objective for the news vendor problem in general is to determine the value of H, right? So my overall objective when we started was determine this value of H. And so our Monte Carlo simulation that we created executes only for a single value of H. And so we would have to institute some type of search function if we wanted to find the best value of H. I'd want to execute my simulation for various values of H and compare the results. And this is discussed in the book, and this is also done in the Excel sheet. For this module, I will leave that as an exercise for you.